Have you ever wondered what invisible force is holding Earth back? Why this massive planet, for all its power and complexity, cannot grow a single mountain taller than 10,000 meters? Because out there, in the vastness of our solar system, tall mountains are not rare. On Mars, Olympus Mons towers at 21,229 meters. On asteroid Vesta, Rhea Silvia stretches nearly 22,500 meters into space. These numbers aren't just impressive, they raise a strange question. Why is Earth so modest? We often speak of Mount Everest as the roof of the world. At 8,848 meters above sea level, it has become a symbol of greatness and of human conquest. But here's the truth. That number includes the elevation of the Tibetan Plateau, which already sits over 5,000 meters high. The summit of Everest only rises about 3,500 to 4,600 meters above its actual base, depending on where you start measuring. In fact, if we go by total height from base to peak, Mauna Kea in Hawaii is taller. It stretches more than 10,200 meters from the ocean floor to its summit. But because most of it lies hidden beneath the Pacific, Everest keeps its title, in name only. And if you think measuring mountain height is just a matter of topography, then perhaps you've never touched the deeper laws of physics that govern the very bones of our world. Because the height of a mountain is not just determined by how big a planet is, but by how heavy. Earth, the most massive rocky planet in the solar system, also has the strongest gravitational pull. And gravity, though invisible, has one stubborn rule. The taller you build, the harder you fall. As a mountain grows taller, the weight of its own rocks increases. That weight presses down on its base, compressing it, squeezing it, crushing it. But rocks, even the strongest kinds, have limits. When the pressure from above grows too great, the rocks at the bottom begin to deform. They crack, they shift, and eventually the mountain collapses under its own ambition. According to geological models, the pressure at Everest's base is already approaching the upper limit of what granite, its core foundation, can withstand. If Everest were to rise several thousand meters more, its structure could no longer hold. It would buckle, bend, crumble, like a tower of stone collapsing under its own weight. In other words, mountains on Earth can be taller, but gravity says they may not. But gravity is not the only force at work. Earth has another, more silent power, one that never rests. Time, winds, rain, glaciers crawling across slopes, earthquakes shifting the crust. All of them chisel away at mountains in the slowest, most patient way imaginable. You could say that Earth sculpts its peaks with invisible hands, shaving off ledges, smoothing out edges, carving deep ridges into once proud giants. So even if a mountain begins to rise, it is never allowed to keep all that it gains, because erosion takes its share, bit by bit, year by year. And beneath every mountain, there lies another secret. The crust is thinner than you think. Only about 40 kilometers thick, Earth's crust floats atop a sea of molten rock, the mantle. Imagine a wooden board drifting on the surface of a boiling lake. Now place a massive stone on one side of it. What happens? The board sinks where it bears the weight. That's exactly what happens when a mountain forms. As it grows, its base presses deeper into the mantle below, submerged by the very mass it carries. This process is called isostatic balance. For every meter a mountain rises above the ground, part of it must sink below, like an iceberg in the sea. So no matter how high the mountain appears from the surface, Earth quietly pulls it back down. Not through violence, but through quiet equilibrium. Now let's travel to Mars. Its gravity is only 1/3 of Earth's. Its crust is thicker. There's almost no rainfall, no plate tectonics, no oceans to carve the edges. And so Olympus Mons was free to rise, slowly, steadily, for 2 billion years, without fear of collapse or erosion. Its height is not a miracle. It's the absence of resistance. And then there are white dwarfs. Those collapsed stars so dense, their gravity crushes everything into near flatness. On such celestial bodies, a mountain can't even rise above 1 meter before being compressed into the surface. Suddenly, Earth feels gentle. Back here, some geologists believe that 10 million years ago, Everest may have been much taller, perhaps even reaching 12,000 meters. But over millions of years, gravity pulled it down, weather wore it away, and Earth's crust quietly adjusted to keep things balanced. And yet, Everest is not frozen in time. It still rises. By about 0.3 centimeters per year. A number so small you'd miss it, unless you were paying attention. But maybe that's the point. Because even on a planet governed by limits, shaped by erosion, held down by gravity, something still climbs. Perhaps what makes Everest remarkable is not that it's the highest, but that it still tries, quietly, persistently. It stretches toward the sky. And maybe that's a truth we often forget, that not all limits exist to stop us. Some are there to shape us, to hold us steady, to remind us that rising slowly, rising within constraint, rising against resistance, is still rising.